Hello, my name is Harvey Molino, and if you've been watching this series, you'll know that I've been presenting little snapshots of what to expect in a G4 session. If you're new to this, if you've just tuned in, as it were, then what I'm doing is giving little snapshots of what one might expect to see when they attend a John M. Campbell gas conditioning and processing course, what we call G4. Today we're going to talk about heat exchangers. In the heat exchanger section in class, what we do is at the end of such a session, you will be able to identify heat exchanger types and applications on a high-level basis. You'll be able to discuss the key variables that affect the overall heat transfer coefficient. We focus mostly on shell and tubes in this section. You'll be able to explain the importance of temperature approach and its effect on heat exchanger area, and that is a critical thing that you need to understand. You'll recognize the basic mechanical TEMA, or Tubular Exchanger Manufacturers Association, characteristics, which will enable you to communicate with a colleague halfway across the world without trying to fumble for descriptions. You can just say, hey, John, I have a type NEN exchanger, and John will know exactly what you're talking about. And you will also be able to discuss fluid placement and fluid flow direction for shell and tube heat exchangers. Today, what I'd like to do is give you a brief overview of the rate equation, Q equal UA delta T mean. I'll describe to you what this rate equation is all about on high-level terms, and then ask you a question. Q is the heat transferred from one stream to the other. It's called the duty. It's the rate of heat transfer. U is the overall heat transfer coefficient. It's essentially the inverse of the resistance that the heat faces when it's going from one stream to the other. The A is the surface area of your heat exchanger, and your delta T mean is your driving force or your mean temperature difference. The driving force is the temperature difference at the hot end of the exchanger, delta T2, and the temperature difference at the cold end of the exchanger, delta T1. This is called the cold approach, and this is called the hot end approach. When we use this log mean temperature difference in order to get an average temperature difference between the two streams. This is the guiding principle, this rate equation, to determine the area of a heat exchanger. So let's take a look at this and look at the resistances to heat transfer. These resistances to heat transfer, if you remember the equation, Q equal UA delta T mean, what we are talking about right now is how to determine the overall heat transfer coefficient U. This slide shows all the resistances to heat transfer. So what we start with is a fluid being cooled. The fluid that's being cooled is being cooled from temperature T1 to temperature T2. We have on the other end of the heat exchanger a fluid being heated. That fluid is being heated from a temperature of little t1 to little t2. The heat that is transferred from the gas that is being cooled is equal to the mass times the enthalpy change, or it could also be equal to mc sub p delta T. The fluid being heated is equal to the mass of the liquid times the enthalpy change of the liquid. And those two heats that are being transferred must be the same. So you can use your enthalpy balance, which we discuss in Chapter 8, to determine what the process requirements are of your heat transfer to determine what Q is. Now what we're trying to do is figure out what the overall U is. Remember, this is going to be equal to U A delta T mean. This is the rate equation, and the rate equation has to equal the heat transferred in the fluid. And this slide is focusing on the determination of the overall heat transfer coefficient. In order for the temperature to go from the hot gas that's being cooled, it has to go through a gas film. So there's a resistance that the gas film offers to the heat transfer. There is also a big resistance that's being offered because of corrosion scale and buildup on the pipe walls. This corrosion scale or fouling creates a very large resistance to heat transfer, as can be seen by this very small sloping curve over here. You had the metallic wall that offers a resistance to heat transfer, which is a function of the thermal conductivity of the metal that is being used in the heat exchanger. And you have a liquid film on the liquid side that also offers a resistance to heat transfer. If you sum all these resistances up and take the inverse of it, that gives you the calculation of your overall heat transfer coefficient, U. So what you end up wanting to do, if we remember our equation where Q equal U A delta T mean, you want the U to be small. You want the U to be large. A large U with a fixed Q is going to give you a small area. And area is what you have to pay for. So you are striving to get a large overall heat transfer coefficient, which is a low resistance to heat transfer. And during the G4 course, what we do is we talk about how to evaluate the overall heat transfer coefficient. We go into what determines the overall heat transfer coefficient, and you will be able to recognize in your facility conditions that you may be able to adjust in order to increase the overall heat transfer coefficient and get better service out of your exchangers. The next time we meet, we will be talking about pumps. Until then, I'll see you at that time.